Hey guys, today we're going to be talking about a fun mathematical concept called symmetry. Symmetry is a mathematical concept where an object remains invariant after being subjected to some sort of transformation. The object can be reflected, rotated, or any other transformation that leaves it unchanged when altered. As explained in the textbook, a symmetry of an object is a rigid motion that moves the object back onto itself. There's more than just shapes that are symmetrical. There are many examples of symmetry in the real world. There's rotational symmetry, reflectional symmetry, and both of these types have many examples that can be found in real life, which we will be looking at today. One place that has many examples we will be looking at in this class is symmetry in the ocean. So as we know, the ocean is full of real-life examples of rotational and reflectional symmetry. So now Mac and Michaela are going to take us away with reflectional symmetry.
Now on to reflective symmetry. Reflection can be described as a transformation representing a flip of a figure. Figures may be reflected in a point, a line, or a plane. When reflecting a figure in a line or in a point, the image is congruent to the original image. An easier way to understand reflection would be geometric transformation in a shape that results in a mirror image. In reflection, every point is the same distance from the central line. There are horizontal, vertical, and diagonal reflections, always starting from the middle line. When you reflect a point across the x-axis, the x-coordinate remains the same, but the y-coordinate is transformed into its opposite. A reflection is completely determined by its axis and by a single point image P and P1. Mackenzie will now provide examples of reflective symmetry.
Usually, reflective symmetry is often seen through shapes, yet it can also be shown in our everyday lives. For example, the mountains can reflect on the body of water found beneath it. In this image, there is a clear demonstration of symmetry reflection, where the line of symmetry is depicted as the line that separates the mountain and the water. If we were to fold the image at this line, we would not be able to notice a difference, which means that there is a clear demonstration of symmetry reflection. If we were to take 1 point from the mountain and 1 point from the mountain depicted on the water, the distance from that point to the symmetry line would be equally the same. Another example of reflective symmetry would be the starfish. If we were to draw the symmetry line right down the middle of the starfish and invert both sides and the left and the right sides, we wouldn't tell a difference, which means that there is a clear demonstration of reflection in this image.
So another example that we see in our everyday lives is symmetry and faces. A lot of people seem to believe that our faces are symmetrical, yet only a small portion of the population have symmetrical faces.
Alright, so now I'm going to try to make my face symmetrical. This would be a symmetrical face. Clearly, my face is not symmetrical.
All right, now let's look at rotational symmetry, and we're going to look at the properties to see how it's different from reflective symmetry. So an object has rotational symmetry when every time you turn the object never changes in appearance as if it was never moved. Let's look at a pentagon, for example. A hexagon has a rotational symmetry of order 6 because we can turn it 6 times and it looks exactly the same as its starting position. The hexagon turns 60 degrees to make each order of rotational symmetry, and this is called the angle of rotation. So to find the angle of rotation, you divide the identity motion, so 360 degrees, by the order of symmetry, which is 6, which gives us 60 degrees. So it turns 60 degrees to get the same. Find rotational symmetry. Let's go into more properties. So the first one is that a rotation is determined by 4 points, so 2 points and their respective images. So we have points P and P, Q and Q. And then where these two bisectors meet is the rotocenter. So this brings us to the second property of rotational symmetry, which is that for there to be a rotational symmetry, there has to be a rotocenter. So the rotocenter is at the center of the image, and it is the only fixed point of a rotation. It is the center of rotation. And then once we find the rotocenter, we can find the angle of rotation. So the third property is that a rotation is a proper rigid motion, so meaning that if an image is rotated, the left, right, and clockwise, counterclockwise orientations will be the same. So let's look at, in the textbook gives the example of mittens. So a reflection does not have a rigid motion because the reflection of a left mitten makes a right mitten. But if it had rotational symmetry, a left mitten should remain a left mitten on the other side. And then the last one, a 360-degree rotation is the identity motion. And this is important to help us find the angle of rotation. Now, let's have a look at some rotational symmetry in the ocean.
So, now taking another example of something from the ocean to do symmetry on, we'll be taking the starfish here as an example. Its rotocenter can be found right here in the middle, and the order of symmetry of the starfish is 5 because we can turn the starfish 5 times and it will look exactly the same as it did in its starting position. So the starfish turns 72 degrees to make each order a rotational symmetry.
So another example we can find for rotational symmetry in the ocean is the jellyfish. Its rotocenter can be found in the middle, and then its 2 points A, B, B. So its axes are right here. And the order of symmetry of this jellyfish is 4 because we can turn the jellyfish 4 times and it will look exactly as it did in its starting position. And the jellyfish turns 90 degrees to make each order of rotational symmetry. So 90 degrees, and then we turn in, it looks the same. And the circular shape of the jellyfish around the fluorescent floral shape in the center also has a rotational symmetry because a circle has an infinite number of axes of symmetry.